that this is something which is happening in the brain, this reactivation. So E stands for excitation. It also can stand, well, if somebody really, when I die, of course. It can stand for my name because L.E. Ashberg, and excitation has exactly the same number of letters. And actually, L.E. Ashberg alphabetically precedes excitation, if you check that. So it's, okay. So anyway, this machine this was a real hacking project because I did enormous, I'm a system engineer consulting, I do a lot of projects for money. I did 3 projects for government, United States government, for money, but I could never get a penny for this project because, so this is a real hacking project which done completely as a private investigation. And I'm now beginning to really, because technology came, that you can really implement these stupid algorithms. These algorithms are enormously memory hungry. That's why, for example, even 10 years ago, it would be stupid to go this way. But now it is not. And I'm saying that actually, that's my hunch, that we will see in certain time, we will see the system because they will certainly outperform this von Neumann architecture for pattern recognition, for all the surveillance things which you're so afraid. But I'm more concerned with the other implication, that really if we understand how our brain works and how we can be brainwashed by putting this, and how we can be mentally reactivated in this stupid way. And if we understand all that, it would be much more difficult to brainwash and to reactivate us, to create a mental set, so we will be much freer. So I think it's very, very important to understand how our brain works, not make all these kind of religious illusions or whatever, but really understand that we are systems, and it doesn't diminish us, because this system is probabilistic, which means it has free will. It can come anything. I think these robots will share some world with us. Okay, I'm almost finished, but I just want to show you that, yeah, you will see it on my website, or it will be distributed as PowerPoint, so you can go deeply into that. So I would say learning is evolutionary development. Then I'm actually comparing, how can it be that simple system? Do we have examples that simple system can produce enormously complex behavior? Sure. For example, I compare it with this Maxwell equations. Maxwell equations are enormously simple, but they produce enormously complex behavior just because they interact with more complex external systems. So that's what I'm saying. And there is a good analogy, in fact, at this general level between this approach, which starts with simple structure, which has only basic constraints, and then by interacting with enormously complex external constraints, it becomes complex. So it is doable. Then, okay, I'll talk about symbolic, non-symbolic, that you really cannot separate symbolic and symbolic. So, and then I go to neural implementation, and I actually show you the cerebellar network. It's something real in our brain. The network is only 3 layers, the cerebellar network. And the network in the cortex is only 6 layers. So if you take this seriously, how this simple system can do what I'm doing now, for example. Or even what you're doing now. You're listening and pretending that you're understanding what I'm saying. So this is, and this is done by this simple system. Let's take this seriously, which means it really, this mother nature is so smart that it found this super efficient integration of these simple things, which work that way. And I liked it this way because nature always does these tricks. And this Maxwell equation is only 4 simple laws, and you get all the variety of electromagnetic. So this one, then I'll show you how you actually can implement the architecture, which I showed you in a way very similar to the cerebellar. And in case you have very large network, But then I actually go, this is output memory, this is input memory. So, but then I actually go to more interesting point at the hardware level. I'm saying that, in fact, everything is not really in a neuron itself, but much more goes to molecular level. And then I come with this, okay. So cells, in fact, evolution spent more time developing cell than developing brain. It took billions of years to develop cells. But then it just did like that. Brain was something like 50 million years old after cells were created. So it's simple. It's another indication that it's not so complex. Okay, that's neuron. All cells are organized on the same level, but neuron has these special proteins sitting in the membrane. So they're different by shape and by type of protein. And here I come with this idea that actually this protein molecule is this probabilistic machine. And you can develop this very well, and I have an article on that. And then you can get, I'm not going into that, then you can get implementation of this memory, which this dynamical memory, these E-states. You can view them as these conformations, relative occupation numbers of conformation in these machines. So it really goes deep. All of a sudden, just starting with this high level, you go to a very low level, and everything fits well. Okay, and then you actually get that these protein molecules, and just by throwing these molecules into membrane, you get computer. You can prove that you get mixed signal computer just from that. So in fact, in a single neuron, you can have that type of functionality. But again, I'm just jumping. And then, okay. That's a simulation of the patch clump experiments. Well, it probably means nothing to you at this point. That's simulation, this Hodgkin-Huxley experiments, how neuron produces pulses. This machinery works. And then it shows what is actually, when you read neural network literature, you read about synapse as a weight, right? And there is nothing further from the truth. This is borrowed from Kandel, who got Nobel Prize for studying aplysia. And that is what is in a single synaptic terminal, all that complexity. So, okay, so I finished. So my final desire that young and talented people like you would really, who can hack anything, would really start hacking this system. It's really a good hacking project. Any questions? Any questions? Okay, probably I didn't give you enough information to ask specific questions. So my goal was just to kind of give you some initiation on that, so you may look deeper and...
Okay, yeah, thank you. I have a question.
Yes. Oh.
I have just one question. Thank you for a very interesting speech. I think for the last 50 years, we've been told that artificial intelligence is about 5 years away. So I'd like to have your opinion on the subject. Like, do you believe that artificial intelligence, like a machine capable of passing a Turing test, for example, is feasible at all in principle? I mean, are you aware of any fundamental obstacles? And do you still believe it's 5 years away?
Well, you see, first of all, I'm not a big fan of artificial intelligence per se. I think it's a kind of playing with words. What is intelligence, in fact? But I do believe that machines capable of simulating the brain are not far away. Yeah. If this is artificial, I wouldn't call it artificial. Artificial intelligence was a kind of more like commercial ploy to me, just claiming something which other people don't claim as good, just some good, smart programming, but not so much better than any other programming. So that's my attitude to that.
If you do believe that we will be able to simulate the brain, do you also believe that at some stage we will get into processing power singularity, which would mean that by being able to simulate minds, we could accelerate the science development in that way that the time needed for example, doubling processing power will always get cut, and in that way that at some stage the processing power rises exponentially, making that if we say 1 year ahead from that point, that there will be no 1 year ahead, because processing power will rise that quick that yeah, a singularity like a black hole in extreme dense form will come, and
you never can tell how people will use technology, but I do believe that certain processes, mental processes, which we would like to accelerate, we may not even want to accelerate it because we want to keep this kind of our privilege to enjoy this mental process.
Well,
but
some like to
we will be.
But I think many also want to use this for military purposes.
And it for sure will be used. That's probably, unfortunately, will be the first place where, if we really make these robots, which kind of what's called universal learning, autonomous robots, so probably military, of course, will use it. But it probably will take some time before robots will be smarter than people. So I wouldn't worry about that at this point. So, but I'm more interested in actually how we can benefit from understanding how the brain works, how we can benefit in improving our own brains, becoming better users, like kind of learning how to learn and learning what to learn. I think that would be kind of, to me, a more interesting thing.
To my understanding, the question of initiative is crucial for the question of intelligence. And as I see it, this neural network modeling only isolates this point and makes it obvious that it's a crucial question. Where does the initiative to learn something, or more specifically something new, where does it come from?
That's a perfect question. And I actually showed you two systems which are needed for universality. This is sensory motor system, which was driving this robot's sensory motor devices. I showed you another system, that's my hypothesis, that there is another system which is motor sensory. It gets motor signals on the input and produces sensory, which simulates what we see and simulates how we see external world. But there is certainly the third system, which is, say, sensory, emotional, which learns to associations between input sensory events and what is present in this moment on our centers of emotions. You know that in the brain there are centers of emotions. They were discovered by Megun and Oltz. That actually, if you take a monkey, and there was an article.
We're running out of time.
Oh, okay. So anyway, if you form this third system, which forms this motivational software, and you interact this system with this two, especially with motor system, then you get this architecture with motivation. So that's my answer to you.
So there's no secret about initiative in your eye?
Well, initiative is just complex